It's my pleasure to welcome tonight's speaker, Dr. Shane Larson. And this will be the third talk that Dr. Larson has given for the geologists at Jackson Hole. His first and second talks were 1 year ago, February, outstanding talks about gravity waves and the LIGO detector. And also his second lunchtime talk was about the evolution of the elements that make up all of the matter in our universe. And both those talks were recorded and are available on our website. I have actually watched them there, they're terrific. Dr. Larson is a research associate professor of physics at Northwestern University, where he's the associate director of CIERA, which stands for the Center for Interdisciplinary Exploration and Research in Astrophysics. He works in the field of gravitational wave astrophysics, specializing in the studies of compact stars, binary stars, and the galaxy. He works in gravitational wave astronomy, both with the current ground-based LIGO detectors and hopefully soon the future-based space detector. Dr. Larson grew up in Eastern Oregon, was an undergrad at Oregon State University, where he got his Bachelor of Science in Physics in '91. He got his PhD in Theoretical Physics 1999 from Montana State University. He's an award-winning teacher, a fellow of the American Physical Society, and a terrific lecturer. He currently lives in the Chicago area with his daughter and cats, and he contributes regularly to a public science blog at rightscience.wordpress.com. If you want to follow him on Twitter, it's @ScienceJedi. And without further ado, I want to turn it over to Dr. Larson, and let's learn about the Milky Way.
Okay. Well, thank you, Mike, for the introduction, and thank you, everyone, for being here. It's a great pleasure to be back talking to the geologists at Jackson Hole. I grew up in the Rocky Mountain West, and so I'm very sad that I'm not there talking to all of you in person, but we will one day be back together again. So what I'm going to do tonight is talk to you about the Milky Way. And as Mike said or reminded you, when I talked to you last year, I was talking about the gravitational wave discoveries. And gravitational waves are very certainly the core of my research.
I want to read the whole damn thing. Don't do that.
The Milky Way galaxy. And that's really going to be the theme of our story tonight, is that much of what we've learned about the universe and much about what we think we know about the distant universe, we have discovered through studies of our own home galaxy. So here in the background behind me is a picture of the Milky Way. This is roughly what you'll see at this time of year if you go out. This is a picture I took at Tony Grove Lake, which is kind of between Logan and Jackson Hole, up there on the ridge going over to Bear Lake. But what the Milky Way looks like to the unaided eye, if you're far from city lights, and for many of us who are from the West, we're used to this sight, particularly in the summer, is this diaphanous band of light that stretches across the whole sky. And what's remarkable about this is that for most of human history, we've had no idea what this is all about. We've only actually known what the Milky Way is for about 400 years. We'll talk about that. And in fact, we've only known a little bit about its properties and what its nature is in the context of the entire universe for less than a century. And that's really one of the most remarkable things to me about this whole story, is that in the context of people you may know, there are people alive today who were born before we actually knew what the Milky Way was all about in the context of the universe at large. Okay, so let me start some slides. So the slides are, I'll provide them. I'll provide a link to the geologists at Jackson Hole, so you'll see them certainly in the presentation, but if they would like to share them on their website so people can go back and study them, that's certainly welcome. My contact information is there. We'll certainly have Q&A at the end, but if 2 weeks from now you suddenly wake up in the middle of the night, or you're standing in your backyard looking at the Milky Way, and you have some question you wished you had asked, certainly feel free to email me. I put the email there for a reason. There's my social media links. And we'll kind of spend some time tonight talking, and we'll tell you a little bit about the Milky Way and our history about it. But then at the end, I'm going to tell you just a little bit, a tiny bit, about what my group does. Okay? So this is a view of the Milky Way that no human has ever had. This is the view of what our Milky Way would look like if we could stand outside of the galaxy and look back at it. It is a view that we have determined by studying the Milky Way from our own location. The sun is embedded in the Milky Way and only about 27,000, almost 30,000 light years out from the center. But we have mapped the Milky Way, we have studied its motions, we have studied its composition, and we have looked at other galaxies. And as a consequence of putting all of those studies together, we have synthesized what this great home of ours might actually look like if we could stand far away and look at it. The beauty of modern art is that it gives us the ability to render it in a way that does not look unfamiliar. Those of you who have looked at astrophotography of galaxies will recognize this as being the kind of colors and the kinds of structures and the kinds of shapes that you're used to seeing if you look at astrophotography of galaxies. Now, what I was saying about our understanding of the galaxy is really that what we know about the Milky Way is almost completely defined by the questions that we can ask about it. And the whole process of astronomy is about going out and finding the answers to specific questions. There are always going to be questions that we can't answer, or questions that we ask and may not be able to answer for decades or centuries. But nonetheless, the questions we ask about the galaxy and the answers we get to them are the things that define what we think we know and define the boundaries of what current modern research about the galaxy is all about. And so the way I'm going to structure the talk here is I'm going to structure it through a series of these questions that we have attempted to answer. Okay? Now, most of you are in Jackson Hole, I assume, at the moment, so you can certainly experience the Milky Way for yourself. If you're in the city, you may have to get away from the lights a little bit. But at this time of year, when it gets dark, roughly around 10:30, 11 o'clock, you will see the Milky Way rising over the eastern and southeastern horizon. It will, over the course of the night, move across the sky until the middle of the night. It will stretch overhead from the northern horizon to the southern horizon like a gigantic backbone supporting the sky overhead. And this is really the view of the Milky Way that humans have had on the Earth for thousands and thousands and thousands of generations. And for most of that time, we've had a name for it. We've called it the Milky Way, or at least in English, we've called it the Milky Way. And we haven't known what it is. It's just a band of light. If you've ever gone out and taught your neighbors or your kids or your relatives stargazing, then some of you may know that the first time you encounter the Milky Way from dark skies like you have out there out west, people often regard it as being clouds. They're like, oh, we're going to get clouded out tonight. Those clouds are there. And it's like, nope, those aren't clouds. That's the light of the galaxy. And so it's always been there in the sky, and we just really didn't know what it was. Much of our historical legends, the mythology about the Milky Way, talks about how it was created, but the mythology, the stories of the Milky Way, don't actually imply what it really is. And what it really is was not discovered until the invention of a piece of technology. And that piece of technology was the astronomical telescope. In 1609, Galileo had heard of the invention of the spyglass by a Dutch optician named Hans Lippershey. Galileo constructed one of his own with what he could find around, what he could make, and from his understanding of its principles. And he was the first person to ever put it on the sky. At that time, it was largely a novelty for the people being used. They were shopping it around to militaries and leaders and things. But Galileo was a scientist, and he had the presence of mind to see what this instrument could do in every possible scenario he could imagine. And the moment he turned it on the sky, he discovered that the sky has far more to hold, far more to tell us than our naked eye alone can show. Now, there are many things that he discovered, and famously, lots about what we take for granted today was discovered by Galileo during this first year. But really, I just want to focus on the galaxy tonight, because what he saw transformed the galaxy. In a very literal way, it made the galaxy. He's the one who discovered it wasn't just a bunch of fuzzy light in the sky, it was actually the light from innumerable, uncountable stars shining down on us. The year after he built his telescope, he wrote a very famous book called Sirius Nucleus. And in that book, it's written in Latin, but there are many English translations, which I'll show you here. In that book, he described what he observed when he turned his telescope towards the light of the Milky Way. Okay, and I will remind you before I read this to you that his telescope was not the greatest telescope in the world. If you just go get the pair of birding binoculars that's gathering dust under your couch and you go pointing at the Milky Way, you will see exactly what Galileo saw, and you will see it better than he saw it, because your binoculars are a far superior astronomical instrument than his first telescope was. What he wrote about the Milky Way was the following. He said, "The galaxy is nothing else than a congeries of innumerable stars distributed in clusters." Congeries is a word that means jumbled, disordered collection. "To whatever region of it you direct your spyglass." He didn't just look in one place, he looked every place he could see the Milky Way. "An immense number of stars immediately offer themselves to view, of which very many appear rather large and very conspicuous, but the multitude of small ones is truly unfathomable." Okay, so Galileo literally discovered the galaxy and was the very first person immediately to realize that there were far more stars in the galaxy than you could ever count or catalog on your own. Today, we know the galaxy holds somewhere between 200 billion and 400 billion individual stars. Okay, it was an enormous collection, far larger than any amount of stars ever counted to that point. The total number of stars visible to your naked eye is something on the order of 9,000 or so. Okay, so the Milky Way is composed of far more of that. Now that is really kind of where things stood about our knowledge of the Milky Way for a long, long time. The growth in the use of telescopes advanced very rapidly. Lots of people acquired them, built them, and began studying the Milky Way. And they were mapping out the stars, they were mapping out the individual star clusters, they were just figuring out what all of these fuzzy things you could see in the sky actually are. But the person who really finally pushed our understanding of the galaxy, thought hard about what the galaxy was Herschel. In 1785, William Herschel decided that he really wanted to map out the Milky Way. For almost 200 years at this point, everyone had been pointing their telescopes to the sky, and they had been looking at all of the stars that the telescope reveals, but no one had sat down and systematically mapped where all the stars were and tried to understand what the shape and structure of the Milky Way was. So Herschel decided he was going to do this. And so he invented a method for doing this, which in principle is no different than the method we use today, but it was a method that he devised because at that time, we really didn't know anything at all about the stars themselves, what made them bright, how to measure their distances, how to measure their properties at all. Okay, but what he did is something you and I could do. We could go out in our backyard with our telescopes and do exactly what Herschel did and map out the Milky Way in the way that he did. So his method is a method called star gauges. And my slides aren't advancing. There they go. Star gauges. Okay, if you want to read about star gauges, you can still read about them. He published his method in 1785 in the Transactions of the Royal Society. You can get it online because you and I live in the future and we have the internet. And if you follow that link down there at the bottom, archive.org, that's called the preprint archive. That's where all of us scientists collect our papers when we first write them so that we can read them before the journals publish them. And this one that I point to right there is a very nice one about Herschel and his studies of the Milky Way. And it kind of describes things in, I think, a way that's very readable if you're interested in that. So what is this star gauges method that he used? Let me describe that to you. So fundamentally, it's about looking at the brightness of stars and deciding that the brightness of the stars tells you something about the distance. Now, the assumption that Herschel made is that every star fundamentally has the exact same brightness. Now, that's not true, but it's close enough to true, or certainly it's close enough to true in that some are dim and some are bright compared to each other, that overall this assumption averages the errors out enough that he could use this method to gain a good understanding about what the shape of the galaxy really was, okay? So to demonstrate his method, I've taken 2 flashlights out in my backyard here. Okay, so I'm standing there with 2 flashlights equidistant from the camera. And the whole point in assuming that stars are the same brightness is that if a star then is farther away from you, it's dimmer. And if it's closer to you, it's brighter. Okay, so in this case, I've taken those 2 flashlights, which initially are at the same distance, and I brought one of them closer to you. And so it appears brighter in the picture. If I do the exact opposite thing and I walk farther away from you, then that same flashlight appears dimmer. I didn't change how much light the flashlight was giving off. I didn't take that 10-watt LED bulb that's in my flashlight and change it into a brighter one or a dimmer one. All I did was walk closer to the camera or walk farther away. And so this was the assumption Herschel made. He assumed all stars are the same brightness. And so if I look at a collection of stars, the dimmest ones are the farthest away, and the brightest ones are the ones that are closest. And by this time, we knew how the brightness of things changed with distance. And so he could use the relative observed brightness of stars to basically map how far away they were when he looked at them through his telescope. Okay, so that's the basic method. Now, to do this, you need a telescope. So he used one of the most famous telescopes in astronomical history. This is called the 40-foot telescope. In those days, telescopes were measured not by the diameter of their mirror, but by how long the mirror took to focus light from one end to the other. So this is from the top of the telescope. You can see there, there's a little cage hanging on the end. That's where Herschel stood. There's a little eyepiece there. He looks back towards the back of the telescope, towards the mirror, and all of the light is focused down towards his eye. So that distance from the cage all the way to the bottom there is 40 foot. The telescope itself was about 4 feet in diameter. So if you have amateur astronomer friends who have big telescopes, that's a little bit bigger than the most common telescope that you see among amateurs today, okay? So what he did was he took his telescope and along 683 different directions into the Milky Way, he pointed his telescope, he counted all the stars he could see in that direction, and he categorized them by their brightness. So ones that were dim, he assumed were really far away. Ones that were brighter, he assumed were closer. Ones that were average brightness, he thought were in the middle. Ones that were super bright were really close. And so he was able to say in that direction, there's a lot of stars, you know, two units of distance away, a few more stars 3 units of distance away, and fewer stars 4 units of distance away. Okay, so he basically could map out the density, the total number of stars as a function of distance from his telescope. And the outcome of that experiment of night after night of staring through the telescope along these 683 lines and counting stars was this map. Okay, this map is the very first map of the Milky Way ever made. And what Herschel wrote about it is a very extensive, branching, compound congeries, jumbled mess of many millions of stars. So think about how many stars he counted along 683 sight lines. Many millions of stars, which most probably owes its origin to many remarkably large, as well as pretty closely scattered small stars that may have drawn together all the rest. Now, he showed in his map here that the Milky Way was a flattened, disc-shaped distribution of stars, which is what we know the Milky Way is today. It's a flat pancake shape. He placed the sun right there at the center. That's the bright one. And every dot in his map here represents some fundamental number of stars. And I meant to look up what that number was and I forgot. But each dot represents some number of stars that he counted when he was looking in that direction. Now, the thing here that I've highlighted in yellow, I think, is really important because 1785, when Herschel did this, was barely 100 years after Newton published the Principia. The Principia is probably the most monumental work in the history of physics. It has the calculus in it, it has the laws of motion in it, but most importantly, it has the first description of how our understanding of gravity, what we call the universal law of gravitation, within it. And that description of gravity was the first time anyone had ever said that every object in the universe attracts every other object. And here what you see is, in less than 100 years, that understanding pervading the scientific thinking, people beginning to understand what its implications are and using it to describe the phenomena they see in the universe. And here Herschel is saying, look, there's a lot of stars, and the reason they're all together at this place in the universe, in this gigantic storm that we call the Milky Way, is that their gravity is drawing them together. Okay, and I think that's probably, to my mind, the most significant thing that Herschel contributed, besides the original observation of the initial shape of the galaxy. Okay? Now let's focus on where Herschel put the galaxy there. So, sorry, one other thing, let me point out here. On the right-hand side of his map there, you'll see that kind of long canyon-shaped structure, okay? So that is actually something you can see in the night sky, so you'll have to wait until kind of midnight, 1 o'clock for the Milky Way to get up high enough in the sky. But if you know your constellations, there's a constellation called Cygnus. It'll be almost directly overhead during the summer when the Milky Way is over your head. And through the middle of Cygnus, there's a place that looks dark. It looks like the Milky Way isn't there. We call that the Great Rift in Cygnus, and it is basically a place where gas and dust in the Milky Way that is not shining is obscuring the light from all the stars behind it. And at this time, we didn't know what those were all about. We just thought it was part of the shape of the Milky Way. It was part of how stars were distributed. But it's interesting to note that it shows up in Herschel's map. When he pointed his telescope in that direction in Cygnus, he couldn't see any stars, and that's why the Great Rift shows up in the map. Okay? So let's focus on the location that he put the sun down there, okay? So where is the sun in the galaxy? That's a really fundamental question, and it's a fundamental question that is probably one of the hardest questions in astronomy to answer. And the reason for that is that the hardest problem in astronomy is measuring distances. Literally measuring distances is the problem with everything you've ever heard about with our understanding of the universe. And it really was, for hundreds of years after the invention of the telescope, the thing that kept us from really understanding more about the galaxy, more about the distant stars, more about the rest of the universe, is that we just fundamentally couldn't measure distance. Okay, well, the ability to measure distance was a puzzle that was solved by a single woman, okay? And her name was Henrietta Swan Leavitt. So Henrietta Swan Leavitt, my slides advance, there it goes. She was one of a group of women who worked at the Harvard College Observatory. Some of you may know her story. There have been some very nice books written about, they were called the Harvard Computers. This was a time where women could certainly go to college, and many women acquired degrees, but they were not really in the workforce the way women are today. They were not treated as equals. They were certainly not paid what men were paid. They did not hold professorial positions, but they're just as intelligent and just as smart as anyone else. And so the director of the Harvard College Observatory at that time, a man named Edward Pickering, discovered that he could hire all of these exceptionally well-trained women with PhDs in astronomy, but pay them pittances compared to what he would pay a male astronomer. And so he hired this very large group of women who are called the Harvard Computers. And among them, there are many famous names. And we could have a multitude of talks about the accomplishments and the importance of these women. But I like to highlight Leavitt because she fundamentally, I think, to my mind, is the most important person in the history of astronomy, because she's the one who discovered how to measure the distances to the stars. In 1912, she had been given the task of studying something called Cepheid variables. So at that time, the Harvard College Observatory, like many observatories, was engaged in collecting as much data about the sky they could. It was photographically recorded on photographic plates, and then the job of many of the Harvard computers was to analyze and look at the data recorded on those plates. And so Leavitt was looking at these particular kinds of stars called Cepheid variables. We won't talk about them. We could have a whole talk about them if we wanted to. But these are stars that basically get brighter and dimmer on a regular pattern. Okay, and she was looking at Cepheid variables in a structure on the sky called the Large Magellanic Cloud. At that time, they knew that it was composed of stars because they could look at it through a telescope. They didn't know what we know today, which is it was a satellite galaxy of the Milky Way. But what she did know is she knew that all of those stars were roughly the same distance away. And so she was able to discover then that because all the stars were in the Large Magellanic Cloud, they're essentially the same distance away from the Earth as every other star in the Magellanic Cloud. And so stars that looked brighter actually were brighter than other stars. And stars that looked dimmer actually were dimmer than other stars. And what she discovered is that if you looked at the Cepheid variables by looking at how their brightness changed, it would tell you fundamentally which stars were brighter and which ones were dimmer. And then based on the fact that she could tell that they were all at the same distance, she could tell there was a relationship between the brightness and the timing that it took them to get bright or dim. And that's the key. That relationship between how quickly they get bright and how quickly they get dim is related to their fundamental brightness. Are they a 100-watt star? Are they a 40-watt star? Is really the key to distance. We call this Leavitt's law today. If you go read about it, it's sometimes called the period luminosity relationship. But what it means is if you find a Cepheid variable anywhere in the universe and you simply time how long it takes it to get bright and how long it takes it to get dim again, that measurement tells you, is it a 100-watt star? Is it a 40-watt star? Is it a 10,000-watt star? And then based on how bright it is in the telescope, you can tell how far away.
Arrêter puis essayer de redémarrer.
On laisse, hein, regardez comme ça, c'est beau.
He's the one who figured it out. And once people realized that they could measure distances only by finding a Cepheid variable, the hunt was on. People were looking for Cepheid variables everywhere in order to measure the distances to the Cepheid variables. If you could locate a Cepheid variable in a cluster of stars, in a nebula, in some structure, then that provided a way for you to accurately measure the distance, accurately reproduce a map of where that object is in the universe. Okay? So the first person to really use this to great success was Harlow Shapley. In 1918, Harlow Shapley worked at the Mount Wilson Observatory, which is on the mountains there north of Los Angeles. At this time, it was the preeminent observatory in the world. He was using the 60-inch telescope at Mount Wilson to observe globular clusters. And so what he was interested in is where are the globular clusters? So he was looking for Cepheid variables in the globular clusters, and if he could find a Cepheid variable in the globular cluster, he could use the Cepheid to measure the distance to the cluster. And so once he knew the distance to the cluster, he could look at all the globular clusters in the Milky Way. There are about 150 of them known, and he could plot where they are in a map in terms of their distance from the sun. So this is a reproduction of Shapley's original map of the locations of the globular clusters. The sun is marked there in the center, the big yellow star, and the green dots are the location of all the globular clusters that he was able to measure the distance to. Now, what Shapley assumed, quite correctly, is that the globular clusters aren't going to be centered around the sun. The globular clusters are going to be centered around the Milky Way. Shapley knew what Herschel had discovered, that the Milky Way was composed of uncountable numbers of stars. So it was the big kid on the block. It was the thing producing all the gravity in this area of the universe. So the globular clusters were going to center themselves on the Milky Way because it was the source of gravity. And so if he looks at the center of the distribution of globular clusters, he finds that it's there where that X is, not where the sun is. So Shapley in 1918 was the one to discover that the sun was not at the center of the Milky Way. Okay, and so that map I showed you at the very beginning that shows the sun out away from the edge, out from the center of the galaxy, this was the beginning of that. Barely 100 years ago did we discover that we the sun and the earth are not at the center of our own galaxy. Okay? Now, this is the time when we were also asking, is the Milky Way the only galaxy in the universe? Okay, and that's a really interesting question to ask, because at this time, there was a large argument about how big the universe was. Astronomers at that time, given the ability to start measuring distances, were just becoming comfortable with the idea that things could be hundreds of thousands of light years away, basically the diameter of the Milky Way. But there was a great debate among astronomers about whether or not the universe could be larger than that 100,000 light year size. Okay, some believed it was, some believed it wasn't. And what you believed was largely based on what data you looked at, and largely based on what your own personal comfort level was with big numbers, where by big numbers we mean numbers like 100,000 light years versus 1,000,000 light years. Okay? So how could this have been a debate at all? Well, it's not that hard to understand. So in the olden days, this is very typical about what things look like when you look through a telescope, either with your eye or on photographic plates. These are both particularly bright objects that you can see in a telescope in your backyard. Centaurus A, you have to get a little farther south or be extremely lucky in where you're viewing from at the latitudes of Jackson Hole. But if you go to, southern Colorado, Arizona, you can get far enough south you can see it. And on the right is something called the Trifid Nebula, which you can see near the center of the Milky Way this time of year, kind of midnight-ish. If you look towards the south, you can see it there in a telescope. Both of these objects kind of look the same. They're kind of white, they're kind of fuzzy, and they kind of have dark striations through the middle of them. Through a telescope, they don't look that dissimilar to each other. So rudimentarily, in telescopic observations, when we were cataloging things in the sky, everything looks like either a cluster of individual stars that you can see with your eye, or they look like dim, fuzzy white blobs. And so dim, fuzzy white blobs were generically called nebulae. Okay, nebula is Latin for cloud. Okay, and these look like clouds in the sky. Okay, so the Trifid Nebula is a cloud. The Centaurus A, we would have called it the Centaurus Nebula at that time. It is in fact not a cloud, but it looks not unlike the Trifid Nebula. Okay, so what's the big debate? What caused people to doubt that these things were just clouds within the Milky Way? The debate was set in motion in 1845 by this telescope. This telescope was called the Leviathan of Parsonstown, okay? So like many amateur astronomers, the person who built this, a guy named William Parsons in Ireland, had what we call aperture fever. So aperture fever is you build a telescope, you can see some cool stuff in the sky, and you decide, I need a bigger telescope so I can see cooler things. And so he built a telescope so big, you can see it there, it's about 6 feet in diameter, that it had to be supported by a castle wall, which you see there in the side. If you go visit Parsonstown today, the castle wall is still there, and there's a replica of the telescope, but the original telescope is no longer there. Parson used this telescope, this 6-foot diameter monster, to look at a galaxy that was then called the Whirlpool Nebula. It was the very first galaxy ever that someone could see spiral structure in. Okay, and this was Parsons' first sketch. In 1872, he sketched the Whirlpool Nebula, as it was called. You can see why it was called the Whirlpool Nebula. But he promptly, and for reasons that historically I still don't understand, he decided that this was what they then called an island universe. Island universe was the name they used to mean another galaxy, because we hadn't invented the notion of galaxies being like the Milky Way at that time. It meant a collection of stars somewhere far across the void, an island in the void of space by itself. Parson promptly declared that the Whirlpool Nebula was an island universe, another galaxy, and this set off what we in astronomy have traditionally called the Great Debate. Okay, so this was 1872, and the debate raged in the professional astronomical community for 50 years. Okay, and the reason it raged is because once people realized you could see structure, once people realized you could measure the properties, not just of the fuzzy ball itself, but the small individual parts of the galaxies, of the nebulas, they began trying to measure everything they could about the galaxy and use their observations, use their measurements to convince people, nope, this thing is really just a part of the Milky Way, or convince people, man, this thing is farther away than anyone could have ever imagined. I know it melts your brain, but that's just the way the universe is, okay? So for 50 years, astronomers back and forth, and we just very robustly divided ourselves into two camps. People who believed the Milky Way was the entire universe, and people who believed that the island universes showed us that there was a much larger universe beyond the boundaries of the Milky Way. This kind of division in science is very typical, and it's very healthy, because what it means is that we don't have enough information, we don't have enough data that we all agree on the quality and the interpretation and the implications of, that we agree on what the story is. This is why science advances, is when we have disagreement on large scales with half of the community on one side and half of the community on the other, that we know we still have lots of work to do. People begin to collect more data, and over time, we all converge until we all agree on what the central story is. There's always people who contradict this or still have new or different results that you don't agree on. But the scientific community, this is how we reach consensus. We collect data, we find data from many different angles, and we find an answer that's consistent with all the data that we have in front of us. So for 50 years, this raged on, and famously, it wasn't going to come to conclusion anytime soon, as near as anyone could tell. And so in 1920, the Smithsonian Institution in Washington hosted a great public extravaganza to discuss what the great debate was all about. It was not unlike the kind of public lectures that you are listening to right now, where they had scientists come to the Smithsonian Institution and talk about their observations and what they thought they meant about the implications about the Milky Way or the nebulae that people were observing in telescopes. And at the end of the day, they had a debate on stage between two prominent scientists, Harlow Shapley, who we talked about recently. Harlow was at the Mount Wilson Observatory, and Heber Curtis. Heber Curtis at that time was the director of the Allegheny Observatory in Pittsburgh. Okay, the Allegheny Observatory is not there anymore. So the two of them basically summarized the scientific debate, and each one of them was actually on one side of the scientific debate. It was, I think, in many ways, the idealization of the way that we like to think science operates, and indeed science operates this way more often than not. We have scholarly debates, we argue with each other, we talk about our viewpoint and our data and things that we have questions about, and then when we're all done, we go have beer and pizza together. Okay, and so Shapley and Curtis certainly were of this mind, and so Shapley was on the side that promoted the idea that the Milky Way was the entire universe, that the nebulae were embedded structures within the Milky Way. And Heber Curtis was on the side of island universes, that the spiral nebulae were in fact other galaxies much farther away than we ever could have imagined. So what were the sorts of things that each of them pointed to? So there were many arguments made. You can certainly go look up stories about the debate and look up papers that were published at this time. But let me kind of describe for you a couple of the kinds of arguments to give you a flavor of the struggle that astronomers were having, okay? So this is an example of the arguments from Shapley's side. So the Andromeda Nebula, when you look at it, you can see it with your naked eye. You can see it spectacularly with binoculars if you go out tonight when it's dark. It's very tiny on the sky. So it's about the size of your thumb if you hold your thumb up at arm's length, okay? And the argument was made that if the Andromeda Nebula was the size of the Milky Way, okay, so at this time we had the Cepheid variables. We could measure the size of the Milky Way. We knew it was about 100,000 light years across. The argument was made that if the Andromeda Nebula, given how big it is on the sky, if it was the size of the Milky Way, it would have to be enormously far away, millions of light years away. And that number was argued was mind-bogglingly large. There's no way the universe could be that big, okay? Other observations that had been made at the time by a Dutch astronomer named Adrian van Manen, he had attempted to measure the speed that the Andromeda Galaxy was rotating. So galaxies, just like our solar system, rotate. And he had measured or had observations that he claimed were measurements of the rotation speed of Andromeda. And if Andromeda was really at those enormous distances far away, then it would have to be rotating faster than the speed of light. Okay, so this was 1920. This was about 15 years after the first description of relativity and the first tests of relativity were shown, that the speed of light was the ultimate speed limit in the universe. And so this was probably the most demanding evidence that this side had, that the island universes could not be infinitely far away. Okay, now as it turns out, Van Manen's observations were in error. Okay, but at the time, our understanding of the data was that they would have been rotating faster than the speed of light, which we knew couldn't be true. The kinds of arguments that came from the island universe side are of the following form. So if you were to stand at one place in the universe and look in one direction on the sky, say away from the Andromeda Nebula, periodically you will see stars explode, okay? So there are super duper kinds of explosions called supernovas, but there are also lighter weight explosions called novas. Novas happen very frequently. We can talk about what causes them if you like. But if you look in one direction on the sky, you can count how many novas happen, say, in a month or in a year. If you then go watch the Andromeda Nebula and you count how many novas you see in the direction of the Andromeda Nebula, what you see is you see many more novas happening in the direction of the Andromeda Nebula than you see happening in any other direction on the sky. Okay, and so the argument was made that novas are events that happen throughout the galaxy. And so when I count a few novas over there and a few novas over there and a few novas over there, those are happening throughout the body of the Milky Way. And if I add them all up and compare them to the number I see over there in the direction of Andromeda, they're about the same. So it must be the case that all of those novas I see in the direction of Andromeda are about the same number as the number of novas I see in the Milky Way, because Andromeda is a galaxy like the Milky Way. Okay, so that's the kind of argument they were making. They're making observational statements. This is what I see. We expect the universe to behave in consistent ways. And so this is an argument that says if the universe behaves consistently, then Andromeda has to be a galaxy. Okay? They were also struggling with something today that we know is related to cosmology, which is if you look at the spiral nebulae, many of them show redshifts. That is to say, they're moving away from our galaxy. And that is actually a consequence of cosmological expansion. It would take another 10 years for them to actually figure out what that was all about. But it was an observation that they knew about at that time. And so it was another thing that was pointed to because the argument was made, why would only spiral nebulae show redshifts? And I look at any other nebulae in the Milky Way and they don't show redshifts. What's weird about the spiral nebulae? So this was an argument that the spiral nebulae had to be outside the galaxy. Okay, so these were the kinds of arguments that were made. And fundamentally, no one could argue against any of these arguments. All we knew is they seemed to tell us different things about the nebulae. And so the only solution to this problem is if you could measure the distance to the spiral nebulae. Well, as it turns out, as we said, shortly before the Great Debate, Henrietta, Swan, Leavitt figured out a way to measure the distances to the spiral nebulae. Okay? And so the person who used Leavitt's law to measure the first distances to the spiral nebulae was this gentleman in the middle. This is Edwin Hubble. At that time, Edwin Hubble was a young astronomer in the employ of Harlow Shapley at the Mount Wilson Observatory. He was using the 60-inch telescope over there on the side and the commissioned 100-inch telescope, which would be coming online right around this time. And together, with other astronomers, he was searching the sky, making an attempt to measure distances, find a Cepheid variable in or around any of the spiral nebulae. And Hubble was the first person to do it. And the spiral nebulae, whoops, I went the wrong direction. The spiral nebulae that he was observing was what was then called the Andromeda Nebula, what today you and I call the Andromeda Galaxy. Okay, so if you go out tonight, it's right over the constellation Andromeda. There's a giant constellation called Pegasus. There's a big square. Some of you may recognize Cassiopeia. The Andromeda Galaxy is kind of halfway between Pegasus and Cassiopeia. And if you go out away from city lights, you should be able to see it with your naked eye, okay? This is the picture that Hubble took. And I'll direct your attention to the upper right corner there. There are two little lines, okay? So that's the way that you marked photographic plates when you saw something interesting. Typically what you would do is you would take a photographic plate, you would wait a week, a day, a month, a year, you would take another photographic plate of the same area of the sky and you would compare the two of them. And when you notice that something changed, you would mark the change on your plate. So those two little lines are marking what he thought was a nova. Okay, so that's the end that he's written there. And you can see other novas that he's marked on the plate as well. Okay, now at some later date, he went back and he crossed out nova and he wrote var for variable star. And that's because he had collected enough different plates of the Andromeda Nebula that he noticed this same speck sometimes got bright and sometimes got dim. It didn't just get bright once and then disappear like a nova did. It got bright and dim and bright and dim and bright and dim and bright and dim. It was a Cepheid variable. And so in 1924, Hubble announced the first measurement of a Cepheid variable in a spiral nebula. He showed that the Andromeda Nebula was about 1 million light years away, about half of the current value that we have today. That value is off because we hadn't calibrated Leavitt's law sufficiently. We hadn't measured enough Cepheid variables yet, but it was the first measurement that showed that very succinctly and clearly the spiral nebulae were not members of the Milky Way. So in the course of a single measurement, the universe went from being just the Milky Way galaxy 100 light years across to being enormous, okay? Far larger than most astronomers had ever imagined it would be. And you can imagine the cognitive dissonance that the scientific community had to come to grips with, because suddenly the universe was far larger than we ever imagined, and these spiral nebulae were far more important than we ever imagined. And so this drove the very large observational effort of spiral nebulae, which was led by Vesto Slipher at the Lowell Observatory, by Milton Humason and Hubble himself at the Mount Wilson Observatory, and led to the announcement in 1929, just 5 years later, of the cosmological expansion of the universe, which led to what we today call the Big Bang, which I talked to you about last February. Okay, so this was the beginning. It's really remarkable how rapidly and quickly paradigms in science shift when the data suddenly becomes very good. And we find ourselves in this position over and over again. It happened in the 1970s when Vera Rubin measured the rotation rates of galaxies and discovered dark matter. It happened in the 1990s when we discovered that the acceleration of the universe was uneven. That led to the discovery of dark energy. It happened in the early 2000s when we could discover that there are exoplanets around other stars. It happened just 5 years ago when we discovered the first gravitational waves from the universe. Astronomy progresses by leaps and bounds when our data gets better. And this is fundamentally one of those examples. Okay? So the last thing I want to talk to you about before I describe a little bit about what my group does is to answer this question. If the universe really is surrounded by galaxies, or the Milky Way is surrounded by other galaxies in the universe, what are our galactic neighbors like, and do we ever interact with each other? The Milky Way has many satellite galaxies. The Magellanic Clouds that we talked about earlier are good examples of those. The Andromeda Galaxy is very similar to our own Milky Way. It's the closest galaxy to us that is similar to the Milky Way. Well, as it turns out, the Milky Way and the Andromeda Galaxy are slowly moving towards each other at about 125 kilometers per second. And in about 3 billion years, the Milky Way and the Andromeda Galaxy are going to collide. If you put yourself in suspended animation for 1 billion years or so, and you go out and do some backyard stargazing when you wake up 1 billion years from now, this is what your night sky will look like. You will see not only our Milky Way, but the Andromeda Galaxy approaching and looking as if it is another Milky Way on the sky. Okay? So we know enough about both galaxies that we can put all the stars in the two galaxies into supercomputers today and simulate what that merger will look like, what will happen when the Milky Way and the Andromeda Galaxy collide. This is a computer simulation sped up very rapidly, but they will come very close together and their mutual gravity will destroy their individual spiral structures. The gravity will pull the two galaxies together, and they will form a very disorderly football-shaped galaxy, something that we call an elliptical galaxy. We see many elliptical galaxies in the universe, and we think this is how they form. They form from galaxies crashing into each other and merging to form a new, bigger galaxy. So this is the fate of our own Milky Way. And if we could stand on the outside and watch it unfold over billions of years, this is what we would see happen. Now, I can make this computer simulation as a view from the outside, but I have very cool colleagues who have done the simulation from the inside. So this is a simulation by an astronomer named John Dubinsky. This is what it looks like from the sun. So that little spot you see there in the background moving around, that is the Andromeda Galaxy. It's moving because the sun is orbiting the center of the Milky Way. So this is us standing on the sun as it's moving, watching the Andromeda Galaxy move across the sky. But as billions and billions of years pass, the Andromeda Galaxy is getting closer and closer together. And eventually, it's going to get so close together that it will become as large in the sky as the Milky Way is. And when that happens, you're going to see that kind of double Milky Way effect that we talked about, where you see two diaphanous bands in the sky. When the orbits of the stars become disrupted, the sun's orbit will also be disrupted. We will no longer be on a circular orbit through the center of the galaxy. We will be on what's called a radial orbit. That is, we're going to be plunging like a yo-yo back and forth through the center of the Milky Way. And so over the course of billions of years, this night sky is going to look very different from the night sky that you and I know. Now, this happens on a time scale of 3 to 5 billion years. The sun, of course, will die in about 5 billion years. Of course, the sun will die in about 5 billion years. The Earth likely is still to be here, so we will be following this orbit with the skeleton of the sun that remains, but we won't have a sun around us to provide energy anymore. But nevertheless, if you can survive on that ice cube of an Earth that is left after the sun dies, this is what your sky will look like over the course of billions of years. Okay? So let me use just the last couple of minutes here to tell you what my group does. Science is contrary to the ideas that we often have about people hunched over their desks in their basements working by themselves. Science is really a large collaborative enterprise. I'm very fortunate to have a large number of really great collaborators. My faculty collaborators are the 4 people listed across the top there. Vicky Caligera is here at Northwestern with me. Matt Benequista, Brett Boland, and Patty Perdue are all colleagues at other institutions. And then the lower group are all of my students. I have both graduate students, they're shown across the top row, and everyone along the bottom row is undergraduates, except for Michael Bueno. Sorry, Michael was an undergraduate. He worked with me one summer, but then he came to graduate school here at Northwestern, so he's now a graduate student as well. And my cat is not a graduate student, but she knows about as much physics as anyone. So, okay, so my group, we work on all kinds of aspects of astrophysics. Most of them are centered around gravitational waves, and a large number of us focus on understanding the galaxy with gravitational waves. And so the way we go about that is we synthesize galaxies on the computer, okay? And so what we mean by that is we create stars at the beginning of their lives, we simulate them through the entire course of their lives, and then we simulate every star in the galaxy. And then we evolve them all through the whole course of their galaxy. So we can study how does the history, the life, the evolution of the Milky Way, how do the conditions under which stars form, all of those things that might affect the Milky Way change what the galaxy looks like today. Because what we want to be able to do is to look at the Milky Way and say, wow, I see this many dead stars, I see this many young stars, I see bunches of stars there and not many stars there. That tells me that the history of the Milky Way went like this. It's not dissimilar to, you know, hanging out at pizza after the astronomy talk and comparing scars on your elbows and knees with all your buddies and saying, I got this one from skiing and I got this one falling out of my treehouse. Your scars tell your past history, even if someone wasn't there to see you fall out of your treehouse, okay? So synthesizing the stars on a computer allows us to understand how the history of the galaxy informs what the galaxy looks like today. So in order to describe how we do this, let me talk about doing it with people first. So if I was doing this in person, typically in-person audiences are about 80 people. You could imagine that I could divide you up by age, okay? So if I were to just guess, right? Maybe there's 10 really old folks in the audience, there's 20 baby boomers, 25 yuppies, 15 college kids, and 10 elementary school kids, okay? If I look at those percentages, they are representative of the total population. So if I wanted to simulate the total population of the country or of Jackson Hole or of Wyoming, I could take those percentages and simulate many more groups of people. Maybe I wanted to simulate 3,000 people in a set that's consistent with the age distribution that I saw there in the room. So here are 3 computer simulations. You see that if I look at, say, the college kids, I always get about 575, 580 college kids. I don't get the exact number, but I get about the same number. And so every one of these simulations is an accurate representation of the number of people, say, in a town, or the number of people in the audience. And I can do the same thing with galaxies. If I pick some properties of galaxies, like age, and I figure how many are young, how many are old, how many are in middle age, and then I use those relationships to synthesize the entire galaxy, I can make an accurate representation of what the galaxy looks like, okay? And so we have, our job as astronomers is to figure out what are the rules that matter. The rules that matter are things like how massive is the star? What does it weigh? Their rules are, is the star born with a partner in what we call a binary, another star orbiting around with it? A rule is, it matters where the star was born. Is it born in the middle of the galaxy? Is it born in a globular cluster? Is it born out in the spiral arms? Okay? How does it live its life and die? What environment does it find itself in? So we have long list of all of these rules. We put them into the computer and we can simulate a Milky Way. Now, we don't know what the life of the Milky Way was like, so we change some of those rules. We say, well, what if fewer stars are in binaries? Or what if more of them are lightweight stars, or more of them are massive stars? Okay, I change those rules, and then I look at how the Milky Way changes. The simulated Milky Way changes. And then I can go compare my simulations to the real Milky Way. Okay, so these are examples of Milky Ways that we make in my group. These aren't the whole galaxy. They are the galaxies just as you would see them in gravitational waves. So every one of these stars is a star that we could see in the Milky Way with gravitational waves. And what you see is we changed how many stars are born in the bulge of the galaxy. Okay, so that's it's a parameter that tells you something about the overall age of the Milky Way. And what you see is the galaxy on the left is much thinner, much more svelte than the galaxy that's on the right. Okay, so we call this thin bulge and fat bulge because it tells us something about the history of the Milky Way. And the day after Lisa flies, when I walk into your living room and throw the Lisa data down on your coffee table, I will be able to tell you which one of these galaxies is the one that's closest to the truth. Okay? So this is really the point then. Our understanding of our home galaxy of the Milky Way changes with our ability to observe it. Our understanding changes with the ability of questions that we can ask and find the answers to. So as our data and our ability to gather data and make measurements of the galaxy improves, our understanding of the galaxy improves, and in fact, it introduces new mysteries and new questions that we don't have answers for. The things that have been discovered in the last 100 years, the fact that the Milky Way is not the only galaxy in the universe, and the fact that it has a certain size, I think are very indicative of how much is going to change in the next 100 years. So if you have grandkids or nieces or little baby kids, right, imagine what we know about the Milky Way today is like us knowing nothing about the Milky Way 100 years ago. And 75 years from now, when someone else is giving them this talk, we will know tremendously different things than we know today, because that's just the way our scientific knowledge evolves. Okay? So I always like to leave you with a few things to read. There are about a gazillion books about the Milky Way if you go look on your library catalog. Because our libraries are closed, I couldn't go look at any of them to recommend any to you, but these are the things that I have on my shelf. You can certainly go look at that Herschel mapping paper at that link there. This book is the book I have about the Milky Way by Bill Waller. It's a very nice book about the structure and what we know about the Milky Way, and this is a Nat Geo documentary that I have on DVD that I really like quite well. So I will stop there and say thank you very much for your attention. I'll leave that up for just a few minutes if people want to write down any of those things. But if Mike or Brent or whoever's going to read questions, I'll stop sharing here and we can take some questions if people have them. Thank you for your attention.
Shane, thank you.
Yes.
Very much. That was excellent and historic. So this is the time when you can type in your questions via the chat function, and then I can transmit them to Shane. While you are thinking of your questions, I want to remind everyone that we have a July program scheduled for July 7th at the usual 6 p.m. It will be the University of Wyoming professor, Dr. Todd Survell, and the title of the talk is The First People and the Last Mammoths in Wyoming. Sure to be fascinating about our own home state. So please send in the questions, and I'm happy to translate them. So Shane, how many galaxies have been observed?
That's a great question. So one of the things that you probably have seen a picture of, there's a very famous picture called the Hubble Deep Field, and various things, Hubble Extreme Deep Field, the Hubble Ultra Deep Field. What those pictures were we asked Hubble to look at a particular place in the sky where we couldn't see anything, and we asked it to do a time exposure for something like 21 days. And when Hubble does that picture, what you see is that those places in the sky are actually full of stuff. And every fleck of light that you see in that picture is actually a galaxy. So the typical Hubble field, if you take a dime and you hold it at arm's length, it's about the size of Roosevelt's eye, okay? And inside that size, on Roosevelt's eye, there's about 5,000 individual galaxies. And so the way we determine the total number of galaxies on the sky is you imagine covering the whole sky in the eyes of Roosevelt on dimes. And so there's something like 500 billion individual galaxies in the entire universe. So it's a big, big number. A brain-meltingly big number.
I have a question, Shane. They talk
Okay.
about local groups of galaxies, and how does the Milky Way fit into that?
Yeah, so one of the interesting things that we've discovered, so when Hubble first started measuring the expansion of the universe, he was basically just looking at galaxies and trying to measure how far away they are. And astronomers have continued that process over the last century. But as we measure more and more galaxies, not only can we measure how far away they are, but we can measure what their relationship is to each other. And one of the things that we've discovered is that galaxies like to cluster together. They congregate. And so if you read old astronomical literature, there used to be a term called galactic clusters. Now, in old astronomical literature, that meant clusters of stars within the Milky Way, what we call an open cluster, like the Seven Sisters is an example of an open cluster. But once we discovered that galaxies actually live in groups, we changed our terminology. And so galactic clusters today, to a modern astronomer, means groups of galaxies that live together. And what we find is that they cluster on all scales. Our group of galaxies is actually pretty small. It's called the local group. There are about 50-ish galaxies in the local group. The biggest galaxies are the Milky Way, the Andromeda Galaxy, and another galaxy that you can see from dark skies called the Triangulum Galaxy. But then there's a whole bunch of smaller ones. So those Magellan Clouds that we talked about are small satellite galaxies to the Milky Way. And if you had looked at that picture of Andromeda that I showed, I can share it again here just so everyone can see. If you look at this picture of Andromeda, this picture of Andromeda here, you see that this small fuzzy dot near the bottom of the screen, that's a satellite galaxy of Andromeda that's called M102. And then if you see the bright center of Andromeda, just up and to the left of that bright center, there's another fuzzy spot that looks kind of like the center of Andromeda. That's called M32. And it also is a satellite galaxy of Andromeda. So the big galaxies like the Milky Way and like Andromeda tend to gather small galaxies around them. But then the local group is about 50 other smaller galaxies than those big three. Galaxies do tend to grow on bigger groups, and so let's see, 20 megaparsecs, so that's 60 million light years away. There's a much larger cluster of about 2,000 galaxies, and that's called the Virgo cluster. And so you can see lots of those in your own telescope as well, but it's the next largest group of galaxies kind of close to us. It's famous for having, many of you probably saw the picture of the black hole they took about a year and a half ago. And that black hole that they took a picture of is at the center of the largest galaxy in the Virgo cluster.
Okay, so this next question, Shane, is really two questions in one. What
Okay.
are the top 3 tools that you use to answer questions about the universe, and what new tools are being developed that will help you understand the universe?
Yeah, so that's a really great question. So my answer to that question, I think, is going to be based on a loose interpretation of the word tool. Okay, so very often we think of tools as being practical things you can hold in your hands, right? And so people might say the telescope or the spectrograph or the camera, right? Those are certainly tools, but I think when I imagine tool, the word tool, I mean something that collects or informs me about a piece of data. And so probably the most prominent tool for almost everything any of us know about astronomy is light itself. And that's because one of the things that we've discovered over the last century is that all kinds of information about the universe can be encoded in light. And if we're smart enough about what to do with that light when we gather it here on Earth, we can break apart those stories and tell you all the things we would like to know about the places in the universe that light came from. Okay, so the most prominent way we do that is we break it into colors, what we call a spectrum. And based on the colors that are present and the colors that are absent, we can do things like tell you what is a distant place in the universe composed of, its composition. If we look at where those lines appear, we can tell you how fast it's moving. If we look at which colors are the brightest in a star, we can tell you how hot the star is, right? So light itself is probably the most fundamental tool, because all the things that you read we know about in an astronomy textbook or an astronomy article in the newspaper, we've discovered by disentangling that story from light. I think the other tool that I would say we're learning to use much more effectively is actually computers. So my group does this, and many groups do this, but I think this is what we do, right? When we collect data, it's telling us something about the universe, but we don't necessarily know all the different things that possibly could have led to that bit of observational data that we have. And so what we do with computers is we take all our knowledge of physics and we simulate the universe, and we look at that simulation and we compare it to our data. And we say, are they the same? And if they are, we're like, interesting. What if I change this over here? What if I change the temperature of the stars? Or what if I change the total number of stars? Or what if I change how fast the galaxy's spinning? Does it still tell me the same thing? And by changing those things in my computer simulations, I can tell what properties of the universe influence how it looks to us today. So increasingly, I think computers are becoming a really important part of the way we understand the observations that we're making about the universe, because they allow us to very quickly explore what the possible implications of a particular observation are. So I would say those two things, aside from telescope, are probably the biggest tools.
Next question, if you're ready for this. Why
Sure.
are galaxies instead of an even distribution of matter across the universe?
Can you repeat that? I missed the beginning of it.
Why are there galaxies, and why instead of an even distribution of matter across the universe? Why is the matter clustered in galaxies?
Yeah. So that is an excellent question. And if you knew the answer to that, we would all be watching you on TV getting your Nobel Prize. Okay, so this is actually the fundamental question in astronomy right now, or one of the fundamental questions. But let me tell you a couple of things that will kind of help put that in context. So when we talk about the universe, we talk about the universe being isotropic and homogeneous. That's the technical language. If you're hanging out around the barbecue with your astrophysicist friends, they'll say the universe is homogeneous and isotropic. What do we mean by that? We mean that in the same way that, I mean, if you imagine you're a grasshopper walking around the cue ball off a pool table, when you look on the cue ball, every piece of the cue ball looks the same. It's smooth and white, and it looks the same in every direction, okay? But if you look on finer scales, you get your microscope out and you look at the surface of the cue ball, it's not uniform. It's got scratches in some places, it's got bumps in other places, but on large scales, it's smooth, it's the same. And so when we talk about the evolution of the universe, we talk about, like what I was describing earlier about counting galaxies, the number of galaxies in that direction on the sky is exactly the same as the number of galaxies on that direction of the sky on these large scales. But on small scales, the universe is clumpy. And the question we would like to understand is, why is it clumpy? And those of you who read about cosmology, you've probably read about the cosmic microwave background. Okay, so the famous observation of the cosmic microwave background that was made in, I guess it was the 1980s now, was that if you look at the cosmic microwave background, it is clumpy on small scales. And those small scales are scales which we think lead to the clumpiness that we see in the universe today, the scales of galaxies. And what we don't know is what causes those initial small scale clumpiness that we see in the cosmic microwave background. That's the $35 million question. And so astronomers like me, we simulate the early universe trying to understand that. Our friends who do observations, they're trying to make even better measurements of the cosmic microwave background. Our friends who look for gravitational waves are trying to look for gravitational waves from the earliest moments in the universe, trying to gather more data to answer exactly that question. Why is the universe clumpy on the scales that we see it clumpy
on? Next question, Shane. Did early astronomers try to use kilometers to measure distances before light years were determined?
Yeah, so the earliest attempts to measure the scale of the universe were actually geometric. Okay, so there's the kind of classic geometric method is called parallax. And if you've taken surveying class, you've experienced parallax, but all of us have experienced parallax in our lives. The kind of classic classroom demo of this is to look at something on the other side of your living room, and with both your eyes open, try and point at it with your finger, okay? And then if you close one eye, and then close it and open the other eye, back and forth, your finger will appear to jump back and forth, okay? But the object in the background appears to stay put, okay? So the idea is then that things that are close, you can measure the distance to them by simply observing them from two different positions. So in the case of your finger, you're observing it first from your left eye and first from your right eye. And because your finger jumps back and forth, you can tell it's closer than that book over on the other side of the room, because that book on the other side of the room doesn't jump back and forth when you open and close your eyes, okay? So astronomers tried to do this by measuring distances with their telescopes. They would look at the position of a star in their telescope, say in September. They would wait 6 months until the Earth was on the other side of its orbit and look at the position of a star in the telescope again and ask, did it jump? Did its parallax, did the direction I have to look in the sky change? And the simple fact of the matter is, all the stars are so far away that no star, at least with a backyard telescope, can you measure parallax with. And so once you start getting to distances are so far away that you can't measure them with this, what we call geometric parallax, it's natural to think about big numbers because you can calculate how big an angle you can measure. And if you can't see a star move by that angle, it means it's really far away. And so people naturally end up talking about light years because the numbers just get too hard to write out that many zeros or those large of an exponents when you're doing things in kilometers. So, but astronomers, you'll hear us switch back and forth. It's just light years are more convenient.
So Shane, I have a couple more questions, and then I'm going to unmute one of our participants because he has a very technical question, which he will translate better than I will.
Okay, fair enough.
Before I do that, what is the oldest galaxy observed? How old is that? And then same question about the youngest galaxy.
Yeah, those are both good questions. So old and young are hard to quantify. So for old, I think it's a little bit easier because what we would say for old is we would look as far out in the universe we can see and ask, what's the farthest galaxy away that we can see? Okay, because the farther away you are, the longer it has taken light to get to us here on Earth. Okay, now the reason I'm kind of hedging on this is because this is a weird statement to make. That galaxy fundamentally is the oldest galaxy, but the light that I'm getting from it came to me from, 7 billion years ago or however long it. So I'm actually seeing the galaxy when it was young in its life, even though it's in principle old today. But in principle, the galaxies that are farthest away are the oldest ones. The youngest ones, that's an interesting question because one of the things that we don't understand is how galaxies evolve over the course of their lives, and how do you quantify the galaxy versus the things that are in the galaxy? Okay, so the classic example that I can give you is to think about the Milky Way. So the Milky Way is a galaxy that is a spiral galaxy, and it is constantly forming stars, right? About 6 to 10 stars are formed every year in the Milky Way. So this is just like the cells in your body are forming constantly. You're sloughing off old cells and forming new cells. The Milky Way is kind of doing the same thing. But when I measure the age of the Milky Way, what part of it do I look at, since it's composed in principle entirely of stars, to decide how old it is? And so that's kind of a hard question to answer. It's kind of long been a puzzle in astronomy about the globular clusters around the Milky Way, because when we look at the globular clusters, which are bound to the Milky Way, and we usually have thought formed with the Milky Way, they're as old as the universe. They're 13.8 billion years. And so that's kind of a conundrum, because when we measure the age of the Milky Way, by almost any measure that we have, the Milky Way is only about 10 billion years old. So yeah, youngest galaxy is kind of hard. So how you measure age is really a function of what you're looking at when you measure the age. So that's an interesting and I think hard question to ask or answer.
So we have about 5 to 6 minutes left. I'm gonna unmute Mike Adler, who has a very specific question, and if you can do a quick answer on why do galaxies rotate, that would also be.
Okay, you mean after Mike's or before Mike's question?
After, I think.
Okay, I'll talk about that afterwards, and we'll end with that question then.
Yeah, so Mike, please go ahead.
Okay, hi Shane, this is Mike Adler. I have a question that has nothing to do with your current talk, but it has to do with gravitational waves, which which you've talked about. And something that's always, I've had this question for some time now. I understand that all gravitational waves that we measure are transverse waves, and they are formed because of some non-spherical disturbance at wherever it happened, like merging of two black holes or what have you. But okay, so here's the problem that I have. Let's assume a perfectly spherical disturbance, such as a black hole, a star having a supernova, and collapsing into a black hole. that is a huge disturbance. And I just assume that there's nothing non-spherical about it. It's just perfectly spherical. That changes the gravitational environment around that object. But you know, someone light years away isn't going to see it. Nothing that change isn't going to happen any faster than it's going to take the speed of light to be sensed. And so and it'll propagate. So isn't that a gravitational wave also? But I'm told that there are no gravitational waves except these transverse waves that occur from non-uniform disturbances.
Yeah. So the technical. Yeah. Are you good?
Yeah.
Okay. So the technical reason, which is complicated to explain, why gravitational waves. So the language we use, if you go read the technical literature, is we say gravitational waves are quadrupolar. They are not monopolar, and they are not dipolar. And it has the kind of ultimate fundamental reason down at the bottom of why this is there's only one kind of mass. There's only positive mass. There's not any negative mass. Okay. The spherical statement's a little bit easier to understand because you don't have to talk about the mass itself. You can just talk about the effect of gravity. And the effect of gravity is that the gravitational force, which in some sense gravitational waves are a manifestation of in what we call the far field, far from the source of gravity, always points in a direct line from the object producing the gravity to the object feeling the gravitational force. Okay, so if you're sitting here on Earth and that star that's about to collapse into a black hole really, really far away is pulling on you, it's pulling you on a straight line towards the black hole. Okay, now the amount of gravity that you feel, the amount of force you feel where you are, is a function of how far away the black hole is, or the star that's going to become a black hole, and how much mass it has. But that's the only thing you can tell about it. You can't tell if it's 250,000 miles across or if it's 2 miles across. The amount of gravity you feel where you are is exactly the same. And that's fundamentally what's going on there when we say that spherical distributions don't produce gravitational waves. I can take that spherical distribution and put it in any distributional shape I want, as long as I'm moving it purely spherical, and you can't tell from far away that the gravity is any different. If you go read about this in physics books, this is related to something called Gauss's law in electromagnetism. It basically says when you're far away from an object, you can't tell anything about the distribution of the matter in that object. And so that fundamentally is what's going on there. The way we typically explain this when we're doing it in classroom, and I can't do this here, is we would draw field diagrams on the board. And if I draw the field diagram for a 10 solar mass star and a 10 solar mass black hole, the field diagrams look exactly the same to someone the same distance away from both of those objects, which is why the gravitational waves why there are no gravitational waves when I turn that star into a black hole. If there's something asymmetric, then the matter is distributed in some funny way, then the gravity is stronger on one side or weaker on the other side because the matter is distributed and you can see or perceive that difference. Gravitational waves are what we call a tidal distortion to the local observations you make of the gravitational field. I don't know if that helps or not.
I think we're going to be ending very shortly, Shane.
Okay.
It's been a terrific presentation. There's a couple seconds left. Maybe you can explain why galaxies.
Why does it rotate? So rotation is, there are many quantities in the universe which the universe doesn't like to create or destroy. Energy is one of them. Momentum is another, and something that we call angular momentum in physics is another. Angular momentum is the tendency of an object that's in rotation to want to stay in rotation. And fundamentally, it's related to the point about which you're rotating and how fast you are moving. Most of you have experienced this if you go out and play hockey and you try and do figure skating moves and you're rotating. If you pull your arms in, you rotate faster. And if you spread your arms out, you rotate slower. This is the kind of classic manifestation of this quantity called angular momentum. So when objects, gas, dust, stars, dark matter, globular clusters, whatever is going to form the galaxy is falling together, it's not all just falling in towards the center. Some of it's falling towards the center, but some of it's kind of falling so that it's going to go right by the galaxy. And when it's doing that, it's feeling all the gravity of the stuff in the center pulling it. And so instead of going on a straight line, if I do it like this, instead of going on a straight line, the gravity is going to pull it. And so it's going to start going this way, but then gravity continues to pull it, and it's going to keep going this way, and gravity is going to keep pulling it. And so it naturally tends into that rotational motion. And that's a consequence of it trying to conserve all of these quantities that nature doesn't like to destroy or dissipate in unusual ways.
Well, Shane, thank you very much for an excellent talk. And that makes 3, and we really appreciate it. And we will see everybody hopefully on July 7th to learn about the first people and the last mammoths in Wyoming. So good night, everyone. Thank you.
Thanks for the invitation. Be safe, everybody.